guys, today we are going to talk about the concept of buoyancy. And so anybody who's been in a pool or the ocean has probably experienced some buoyancy. But this initial question here says a penny that weighs a few grams will sink in water, but a huge steel ship will float. And how is that possible? And hopefully by the end of this PowerPoint, you guys will know the answer to that. And so if you guys have ever been at the pool and tried to push an inflatable raft underneath the water, you discovered it's kind of hard to do that, and that's because the water is pushing back on you with a force, and that force is called the buoyant force. Let's take a look at a couple of examples of that. So, for anything that is submerged in a liquid, right, that object has a couple of forces acting on it. It has its force of gravity, right, however much it weighs pulling it down. And then it also has this upward push that's provided by the fluid. Things like fish or divers, for those kinds of situations, the buoyant force almost exactly balances out the force of gravity. For things that are floating above the water, like this guy here, his weight is counteracted by the buoyant force. So in this instant, we say these things are in static equilibrium when something is floating like that, but we'll get more into that in a second. Okay, so let's talk a little bit more about what it means for something to be in water or a fluid and how that factors into calculating buoyancy. So, whenever you put an object in water, what you're doing is you are pushing out water from that spot in the fluid that I guess would normally be occupied by water. And in that case, if you completely submerge an object here, the amount of volume of that object is equal to the volume of the fluid it displaces. So that kind of makes sense, right? If you've ever taken a bath, well, hopefully you have. If you've ever sat in the bath and noticed that when you get in the water level rises. And that's because your body is displacing the fluid that's in the tub. It's pushing pushing that fluid upward a little bit because your body is occupying the space in the water that the water would normally occupy. This is going to become important because this helps us discover what the buoyant force is, this relationship between the submerged volume of the object and then the volume of the fluid. So the weight, this little thing in here, down here is starred a couple times because it's super important, but the weight of the displaced fluid gives us our buoyant force. So keep that in mind throughout this entire PowerPoint because it's super important. The weight of the displaced fluid is our buoyant force. All right, so let's take a look at a little PowerPoint here. This ranking task. So it says the 5 blocks below have the masses and the volumes shown. Rank in order from least to greatest the buoyant force on the blocks. So again, buoyant force is equal to the weight of the water that is displaced, or the weight of the fluid that is displaced. And the weight of the fluid that's displaced depends on the volume of the fluid that is displaced. So if we look at it here, kind of relationship-wise, if my pen will work. Okay, so this whole idea of buoyancy, you have to keep in mind the relationship of density, right? Density is mass divided by volume. And the buoyant force is equal to the weight of the water that is displaced. And weight, remember from AP1, is the mass times the gravity. But a lot of times we won't know the mass of the water. That's incredibly hard to calculate. So most of the time we will know the density of our fluid. And the volume of our fluid that is displaced is pretty simple to calculate, again, just because it's going to be the volume of whatever the object is that's sitting in the water. So a really common way to think about buoyant force is to say, instead of saying that the buoyant force is equal to the weight of the fluid, and I'm going to put a little f here just so that we know that that means the weight of the fluid that is displaced, but rather to say the density times the volume of the fluid displaced times gravity. Because if we do density times volume, we get our mass. So if we keep that relationship in mind and just plug that in here, this is a better way to talk about our buoyant force. So if we use this mentality, they're all sitting in the same liquid, right? So they all have the same, the density of the fluid is all the same. Gravity is, of course, a constant. The only thing that we're looking at is the volume of the fluid that is displaced and how that differs in each one of these situations. And, of course, the more volume of the object that's in the water, the more volume of fluid gets displaced or gets pushed out. And so, using that logic, this guy would be number 1. All of these guys here would be number 2. And then this one down here would be number 3. Because buoyant force is going to depend on the volume of the fluid that is displaced. All right, so this idea of buoyancy led Archimedes to discover Archimedes' principle. He named it that, of course, after himself. And he says that the buoyant force on a body immersed in a fluid is equal to the weight of the fluid displaced by that object, which is what we just saw on the previous slide. So this is essentially what I wrote for you before. And this is what we term as Archimedes' principle, that the buoyant force is equal to the weight of the fluid that is displaced, because rho times volume is mass, and mass times gravity is weight. So, and there's Archimedes. So, a little bit of an example here for you guys, and this is going to bring back some stuff from AP1. So we're going to go to my little whiteboard here thing so that we can kind of draw it out and talk about what's happening. But legend has it that Archimedes was asked by King Hero of Syracuse to determine whether a crown was made of pure gold. It was this problem that led him to develop the principle that bears his name. If you guys know the story, Archimedes was sitting in a bathtub, and he saw the water displacement when he sat in the bath, and he supposedly shouted Eureka and ran naked down the street because he was so excited that he figured out how to determine whether this crown was gold or not. So, down here in a modern version of his method, we're going to use a crown weighing 8.3 newtons, and we're going to suspend it under water with a string. We're going to measure the tension in that string to be 7.81 newtons. So the question is asking, is the crown pure gold? Keep in mind the idea of density, right? Keep in mind that the idea of density is how we're going to determine whether this is gold or not. The density of gold is 19,300. I'm pretty sure that's kilograms, meters. This is the density of pure gold. So all we have to do is determine what the density of this object is based on its mass and based on its volume. And then we can determine whether or not that density matches up to the density of gold. So let's take a look at our problem. We're going to go keep annotations. We're going to go here and kind of draw it out. Okay, so in order to do this, we have to remember how to draw free body diagrams from our AP1 days. Here's water, here's a string. I'm not going to try to draw a crown. I'm just not good at that, so we're just going to draw a box. So here is our crown, and it's attached to a string, and he's putting it in water. So let's draw a free body diagram for all of the forces that are acting on this crown as it's in the water. We should always put our force of gravity, or our weight, on our free body. It's on every single free body. We also have this upward force in the string, which is our tension. And I'm going to make it be a little bit smaller just because of what I'm about to do. But because this is sitting in a fluid, sitting in water, not only is there a tension force upward, but there also is a buoyant force. So these two should be these two added together should be relatively equal to this, but I didn't draw it that way, so I'll fix that real fast just because it's going to bother me. So we have a free body now. We have three forces acting on this crown. We have its weight, we have its tension in the rope, and then we have its buoyant force. So when we draw or when we write out a net force equation for this, we're going to take the down forces and subtract them from the up forces. So we have the weight, Fg, minus the tension, minus the buoyant force. And since the crown is at rest, it's in static equilibrium, those three things should be 0. Well, luckily enough for us, we know the weight. They told us at the very beginning the weight was 8.3. And we even know the tension force to be 7.81. So all we have to do now is just calculate our buoyant force. Well, let's take a look at that. Our buoyant force, when we do that, should be 0.49 is our buoyant force. So great, we have a buoyant force. We have a kind of a conceptual understanding of where we're trying to go with this problem. We're trying to find the density of the object. That's our end goal. Well, we have the buoyant force, and we know from our previous slide and from Mr. Archimedes that the buoyant force is equal to the weight of the water that is displaced. So that means water has a density of 1,000. So when I plug this into my formula, I get that of our water, whenever I calculate this, ends up being a very, very, very tiny decimal, 4.9 times 10 to the negative 4th meters cubed. This is the volume of our water that is displaced. So, what does that mean? Well, the volume of the water displaced is also equal to the volume of the object that is submerged. And in this case, the entire crown is submerged underwater. So, consequently, this is also the volume of our crown. So, we have the volume, we have the weight of the crown, and the weight of the crown was 8.3 newtons. If you guys don't remember, weight is force of gravity, and that is mass times the acceleration due to gravity. So acceleration due to gravity is 10, roughly, which means the mass of our crown is 0.83 kilograms. Well, we have the mass and we have the volume, so now we can just use our density idea to divide the two. And you end up with about 17,000 kilograms times per meters cubed as your density of your crown, which is not close enough to consider it to be pure gold. All right, so here we go. Danny decides he's going to teach his cat how to swim. Here's another example. Ties a rope around his cat, tosses her into the pool. The cat has a mass of 8 kilograms and an average density of 2,500. And again, I just made this up, so I'm not exactly sure if that is a correct number for the density of a cat, but we are going to go with it. Determine the volume of the cat, and then determine the tension in the string when it's completely immersed. I would like you guys to try to do this one on your own. We will check it together the next time I see you, or later this week. So, A little word on floating versus sinking. When an object floats or sinks, it really comes down to whether or not the fluid density is larger or smaller than the object's density. So if the fluid and the object have the same density, it experiences what's called neutral buoyancy, which happens a lot to fish and turtles and other sea life. But, that's supposed to be hang motionless in the fluid, not hand motionless in the fluid. But it just kind of floats in the center. So here are just 3 different pictures, just so you guys can kind of see. Here's one object where the weight of the object is greater than the buoyant force, and so it will sink. And in this case, the density of the object is greater than the density of the fluid. Here we have an object floating. Here the density of the fluid is greater than the density of the object, and in this instance here, the density of both of them are equal. Alright, so floating objects, fun time. If you release a block of water, of wood underwater, a block of water, the upward force causes the block to shoot to the surface. So the question is that once it's at the surface, then what happens? Well, now it's floating. It's no longer moving. It's not like the water shoots it completely out, right, and into the stratosphere. No. So at that moment where the object is floating at the top, we say it's in static equilibrium, kind of like what I talked about at the beginning of this PowerPoint. And the upward buoyant force exactly balances out the downward weight of the object. So this is another 2-starred point, which is super important to understand. For a floating object, the volume of the displaced fluid is not the same as the volume of the object, because the object is not completely under the water, right? Only a little bit of that object is actually sitting in the water, so that volume of whatever is sitting in the water contributes to the volume of the displaced fluid. So we're going to do a little example on this raft thingy here, so you can kind of get the idea of what I'm talking about. So here we have a wooden raft floating in a lake. It's 3 meters long, 2 meters wide, and 1 meter deep, and its density is 600. So first part is determine the depth of the raft submerged below the water. So the density of the raft is 600. We know that the density of water is 1,000, so of course it makes sense that the raft would float. We just want to know how far is it going to be submerged in the actual water. And then part B says the depth of that it would be submerged if friends would suddenly flooded and all the students in this class had to use this raft as a life raft. And there are 24 students in our class, if you want to pause the video and try to work it out on your own. All right, so the first thing we're going to do is figure out the depth that the raft is in the water when no one is on it. So let's just think about what's happening here. Here, we're going to draw, ooh, that is an unfortunate raft. Okay, we're just going to go with that because I'm not going to re-erase it. All right, here's a raft in the water, right? Some of it will be above the water line. Redraw my water line. Some of it will be above the water line, and some of it will be below. Because the density of the raft is less than the density of the fluid it's sitting in, it is going to float. So let's, again, same idea, even though we kind of know what's happening, I still want to talk about it. We have weight, and then we have a buoyant force going upwards. And again, those two should be relatively equal. So what we know about the object when it's floating is that it's in static equilibrium, and the buoyant force is equal to the weight of the raft. All right, so we have the dimensions of our raft. It said it was 3 by 2 by... And we know the dimensions of the raft, and we know the density of the raft. So we can put those together and figure out what the weight of the raft is. So Let me write this out. So the buoyant force we know is equal to the density of the fluid times the volume of the displaced fluid times gravity. And then the weight of the raft is equal to the density of the raft times the volume of the raft times gravity. All right, so let's do the right-hand side first. Density is 600. The volume of the raft is 3 times 2 times 1, length times width times height. And then gravity is 10. So let's look at the fluid side. 1,000. Now this is the fluid, or the volume of the fluid that is displaced. So the length and the width will be the same, but the height will not be, right? Because we don't know how far, we don't know this height. We don't know how deep the raft is sitting in the water. So we don't exactly know the volume of displaced water yet. So that has to remain our unknown variable in this equation. So we have 600 on this side times 6. And then we're going to end up with 10,000 times 6. Once we do all that math, we figure out that the height is 0.6 meters. So that tells us that 0.6 meters is below the waterline, which means that 0.4 meters sits above, since the whole height of the raft was a full meter. Okay, so same problem, slightly different. Now we're going to add more mass to it. Now we're going to draw our, did it twice. We're going to put people on top of it. So, same kind of idea. Let's take a look at our free body again. Now, since we have more weight on the raft, it makes sense that more of the raft would be underwater, but it's still floating, so it's not submerged yet. So, now we have the weight of the raft, and then we also have the weight of all of the people. And then we have the buoyant force. So again, these forces are going to be equal and opposite to one another. We just have two weights going down now. So weight of the raft plus weight of the people equals the buoyant force. So we already figured out the weight of our raft, right? We said it was, so weight of the raft is density of the raft plus the volume of the raft times gravity. Now the weight of the people, they're already telling us each one weighs 60 kilograms, and we're going to use 24 of them. I won't get on the raft with you guys. I'll let you survive. Okay, so we know that, times 10. Mass times gravity times the number of students that we have, which is 24, and that will give us the total weight of the people on the raft. And that has to equal our buoyant force, which is the same thing as before. Density of the fluid, volume of the displaced fluid times gravity. We actually have a gravity in each term here, so that can just go away. So, again, plug and chug. Our density of raft was 600. Volume was 3 times 2 times 1. We're going to do 60 times 24. And then that is going to equal 1,000, which is the density of water, times 3 times 2 times the height of the raft, some height h here that is submerged underwater. So once we figure all that out, plug all that in, we get a height of 0.84 meters. This is the amount that is below the water, which means 0.16 meters sits above the water. Okay, so here's just a closing question for you guys. Block of iron sinks to the bottom of a vessel of water with a block of wood of the same, while a block of wood of the same size floats. On which one is the buoyant force greater? I want you to just answer it in your head. You can answer it on your paper. But it's very tempting to say that the block of wood experiences the greater buoyant force because it's floating. But remember that buoyant force is equal to the density of the water times the volume of the displaced water times gravity. So in which case, when a block of iron sinks to the bottom or a block of wood floats, here's our water, here's our iron down here at the bottom, here's our wood up here at the top, at which one of these will the buoyant force be greater? Well, hopefully you said the block of iron, because if they're the same size, which the problem tells us they are, all of this guy's volume is underwater, so he will displace more water, so his buoyant force will be greater. The wood is only experiencing, well, we don't know, but not as much buoyant force as this guy, because it's only partially submerged, so only a part of its volume contributes to displacing the water. All right, that's it, guys. I will talk to y'all later.